Hello, Boris and class at Weston High School and other places. This is an interactive simulation of the November challenge problem from the physics teacher, and I thought I'd show you how it works. Okay. What I found, both analytically and from the simulation, is that the cutoff coefficient of friction for this bent plate to stay on the cylinder is about 0.41. So if we set this to anything less than that, and then I'll run the simulation, we can see that it falls off. I'll reset. Okay, I'll move this up to about 0.40. We can see that it slides off, maybe not quite as fast. Reset again, move it up to 0.41. Okay, again, it just kind of creeps off of there, but it still comes off. Okay, move it up to 0.42. And maybe it's just kind of a vagary of the numerical part of the simulation here, but it tends to kind of slip a little bit, at least visually, but then it seems to stay. Same at 0.43, I believe, and maybe a few snaps higher than that as well. Tends to do the same. But anyway, if we put it much higher, it still makes a little visual slip in the event. But the interesting thing I was mentioning on email was that if we take a look at the, excuse me here, if we open the properties of the input here, excuse me. Okay, sorry, that's not quite what I had in mind. Properties of the circle. Okay, what I needed to do to make this work was to make the static friction and kinetic friction both coupled to the slider input for both the circle and the polygon. The polygon is actually the plate. It's actually a six-sided polygon that is bent into the shape of that plate, very, very thin. But that's the way I seem to make it work and agree with the analytical solution of mu being approximately equal to 0.41 or 0.42. So, hope you enjoy this, and Dr. Korsunsky, if you have the file, if you're able to open it up, you can kind of play with it yourself if you're able, if you have time. But otherwise, let me know if this is helpful or not, and hope to be in touch in the future. Take care.